Hello again, I'm K. Mishra, Micromouse lead, and today we will be going over the modified Floodfill algorithm. It's not going to be too long of a presentation. This is pretty short. So, key concepts. Let's go over some of the basics of this maze-solving algorithm. Some of the main aspects and properties that we're going to be utilizing within this modified Floodfill algorithm is using Manhattan distance, checking for minimum values when moving from cell to cell, and flooding neighboring cell values when we are not able to move. So to start off, let's first discuss what are Manhattan distances. So I know you guys know about the distance formula for Euclidean distance, and that's for finding the shortest path between 2 points. Right? So if you have this diagram right here, Euclidean distance, you would calculate, how long is that line that goes from point 1 to point 2, right? Manhattan distancing is a bit different. It finds the shortest distance between 2 points based on unit changes over one axis at a time. What I mean by that is you can only move in one direction, 1 unit at a time. You can't just go diagonally and straight because, in our maze, we can't just cut straight to the center, ignore everything else. So how do we calculate the distance for that? Well, there's a nifty little formula here. Let's say you have 2 points, P and Q. We're assuming this is a 2-dimensional plane. We're not going to be doing 4D or 3D planes, so there's only going to be two set coordinate system. It's P1, P2 for point P, and Q1 and Q2 for point Q. So how do you calculate the distance? Well, you basically take their coordinate values and you do the absolute value of P1 minus Q1 plus the absolute value of P2 minus Q2. Right, so let's say point 1 was located at 0, 0, and point 2 was located at 2, 2. I know it's not actually 2, 2, by the way. I'm just saying for the sake of the discussion. And we want to calculate what is the Manhattan distance between these 2 points. Okay, so then you just do P1, which is 0, minus P2, 2, which is 2. So you get 2. Right, the absolute value of minus 2 is 2. And then 2 plus 2, you get a Manhattan distance of 4. Right? Now, keep in mind, multiple paths can satisfy this distance. To give you an idea, let me just pull up the simulator. Okay, of course. I have to set my environment variables again. Okay, this is another thing you have to do, by the way, whenever you're trying to run Qt. I'll cover this in the end of the meeting. I know one person had a question about, I'm having trouble installing Qt and getting it set up and whatnot. Yeah, I'll be sure to answer some of these questions after the presentation. Okay. So let's see a blank maze. Okay. The center 4 cells, they're all zeros, right? And each of these cells, what they indicate is the Manhattan distance it takes to get to one of the center 4 cells. So this is discussed in my next slide, right? Fill in each cell's value using its Manhattan distance to the closest of the center 4 cells, right? So you can split the maze up into 4 quadrants. Calculate the Manhattan distance for every cell in this quadrant respective to this center point, and do the same for all the other quadrants. So any questions on that? Or is that clear? Okay. Nobody's saying anything, so okay. Nobody's saying anything, so I'm gonna say it's clear. Okay. So minimum value checking. This one's pretty self-explanatory. When you move from cell to cell, check for an accessible neighboring cell. That means a cell that doesn't have a wall in between on the way. Check for an accessible neighboring cell with a proper minimum value. What I mean by proper minimum value is that the minimum value of that cell, of the cell with the lowest value of your neighboring cells, should equal to the cell you're currently on minus 1. In case there's multiple such cells that satisfy that condition, cells directly in front of you are prioritized. By the way, this doesn't necessarily have to be followed. If you want, you can prioritize it in another direction if you really choose to do so, but this is most convenient. And in an actual competition, it's preferred that you prioritize cells that are directly ahead of you so you don't have to turn as much. Okay, so what happens if you can't move anywhere because there's no suitable cell to move towards? Okay, so that's where the flooding part of Floodfill comes in. Right, so whenever the mouse reaches a point where no neighbors are suitable to move to, flooding occurs. So the process is, first you have to check if the minimum value of the surrounding neighbors is equal to the current cell's value minus 1, right? If it is, okay, then you just continue and move on to that cell. If it isn't, you push all the neighbors, all the accessible neighbors, onto a stack. Not all the accessible neighbors, all of the neighbors onto the stack. Even if they're not accessible, even if there's a wall in between you and another neighbor. The only exception is that if the cell has a value of 0, then you do not push it onto the stack. All right, so next, what you have to do is you have to update the cell you are currently on equal to the minimum value you found from your neighbors plus 1. So let's say, I'm on 3 here, right? And I can't access 2 for some reason. Okay, and I can't access this 2. I can only go back, or I can go to this 4. Right, so I would have to update this cell's value to be 4 plus 1. So this cell would then have a value of 5. Right, and then I would push all the surrounding neighbors onto this stack and do that same process until the stack is empty. Right, so let's have an example here. Let's say you're in a pretty small maze. The Manhattan distance, is pretty small. It only takes 4 moves to get to the center, assuming the maze is blank. All right, so we start off on 4, right? Push 0, 0 onto stack here. All right, you detect a wall. So you can't go to this neighbor, but you can go to this neighbor, and it satisfies the minimum value requirement. So you move to that cell 0, 1. Right? And then you reach cell 0, 1, you see that you have a wall up here. Okay, so you can't move there. But this neighbor still satisfies the minimum value requirement, so you move to that cell. Okay? Same process continues, can't move here, can't move here, you can move here. Okay? Now flooding occurs. Why? Well, when you are at cell 1, 2, there is no neighbor which satisfies the minimum value requirement. So now what you do is you set your current cell's value equal to the minimum value plus 1. So in this case, who is the smallest value here of the neighboring cells? So you set current cell's value equal to 2 plus 1. Okay, so this becomes 3. And then you push the neighbors onto the stack. Oh. So here's a catch. There would typically be another neighbor up here as well, but I'm just gonna say I kind of skipped that. That was my bad. The cell in front would also be pushed onto the stack, but it's its minimum value requirement is supposedly met because we don't know anything about what's going on there. So yeah, you push these two cells onto the stack. You don't push this cell, no matter what, because it has a value of 0, right? And then you do that same process until all the cell's values are updated. So what happened here? You push this cell onto the stack and this cell onto the stack. When we push this cell onto the stack, just assume there's another 2 here, right? So the minimum value is 2. So this cell now has to be updated. So this cell's value now has to become 3 because its minimum neighbor is 2, right? And then this cell right here, what we originally started off with, would have to be updated again, right? And this would become 4. As for this cell, its minimum value is 3, so the cell's value would become 4. This cell's value would become 5, and this cell's value would become 6, giving you the map we have here. All right, and then you continue that process until you reach the center of the maze. And this will guarantee that you reach the center of the maze, no matter what. It might not be the most optimal path at first. You're going to have to, take a run back to the starting point in order to find the shortest path. And the number of runs you'll need to take depends on the type of maze you're facing. Okay. So yeah, that's the basics of Floodfill. Again, not very complicated. So are there any questions?
So when we're using Floodfill using the Manhattan distance algorithm, we don't know the distances in advance. So would it just rely on like this relative recalculation each time? Like as soon as it realizes that there's like a more distant value, it just reconfigures everything?
Okay, so what you're asking is we don't know for sure that this is the actual number of moves we need to get to the center, right? Okay, that's fine because whenever flooding occurs, it will update those values for us.
Okay.
Right. Here, let me. Okay, this is also one of the weird things I noticed about the mazes. Mazes already have values in them for some reason. I don't know why. Whenever I start off, it's fine. It's not bugged. I promise. I mean, it can be sometimes. You never know. But okay, so when we first run this maze, right? We don't know any of the walls, where any of the walls are, except for this one, of course. But we don't know where any of the walls are, right? So our mouse, what it thinks is that, okay, I can just go the shortest route right away because it doesn't know that any walls are there, right? So whatever the Manhattan distance is, right, it'll assume it can just follow that and then it'll reach the center, right? But as it detects walls, it'll store them within its memory, right? And then flooding is gonna occur after it moves to the cell right there, right? Look at that. All the previous cells values were updated, right, based on what we discussed, right? And that's gonna occur again. It's gonna keep occurring. Yeah, so flooding will occur whenever it needs to. Whenever the mouse detects, okay, the minimum value requirement is not being met, so flooding needs to occur in order to update these values to properly indicate the estimated number of moves it will take to get to the center. Okay, then we'll head back to the center. sorry, it'll head back to where it started, and then it will head to the center once more. And depending on the maze, the next run you take might be the shortest, it might not be the shortest. So, in order for you to know that, on the path you take, there should usually be no flooding occurring. That's usually how you know that, okay, this is the shortest path I can take because no flooding has occurred. And I'm following all the minimum values. Okay. I keep seeing this update for N2E. Okay. A bit distracting, but whatever. So yeah, Floodfill updates as you gain more information on the maze, and it will be update accordingly based on whatever cells it thinks it can access. Okay, so is there any other questions a bit on how Floodfill works? Anything about, you want to ask about stacks? I could show the raw code as well. So if I go to here, actually I should just open the project file. Okay. All right, whatever. Bigger project. All right, whatever. Okay. Okay, so yeah, here when I'm initializing the map and the walls, the walls are initially set to be what you see here on the blank maze. There's walls on the sides. Right. Oh, my bad. Not mean to do that. Okay. Slow this down a bit. So initially, all the walls on the ends of the maze are set, and the cells values are set based on their Manhattan distance to the closest center cell, and that's for the beginning. And then when it's searching, this is just a little test thing I did because the simulator was bugging out earlier for some reason. Okay. So it checks for the walls as you move along, right? It sees where it can step to using the flood step function. And the flood step function, what it does is it incorporates the flood fill algorithm. Okay, so it takes a cell and the direction you're facing. Cell you're currently on and the direction you're facing. And it calls a function called flutter. Right, so what flutter does is that it creates a stack for cells called flood, and it pushes the current cell onto the stack. Then, while the stack is not empty, you find the cell that's at the top of the stack, you pop it, right? And then you find the minimum value from your surrounding neighbors that you can access, right? And if that value is not equal to your cell's current value, -1, it sets, first of all, it sets your current cell's value equal to the minimum value +1. And then it pushes all the surrounding neighbors onto the stack, given that their flood value is not equal to 0. Okay. And that's how that's implemented. And then eventually the stack will become empty, and then all the cells values will be updated. And then flood step, what it will do is then it will find the minimum index of the minimum value neighbor. Sorry, it will find the index of the minimum value neighbor. Okay. And then your mouse will move to that index. Okay. So any questions on that? anything you would like me to go over, or is like the methodology behind Floodfill a bit unclear? No? Okay. Oh, wait. That reminds me. Okay. So I asked you guys last week what ideas you had for reducing our bot's score as low as it can go. So does anybody have any suggestions for how we might approach that?
I'm not sure. I'm gonna have to go look everything over again.
So let me again, I'm gonna pull my screen. I should just keep my screen on. I don't know why I keep turning it off. Okay. Okay. So if you look at the simulator here, I think this is the right maze. It might not. I think it's maze 3 actually. Nope, it's not maze 3. Maze 4. Which one was it? Okay, no, it's maze 2. All right. So in this maze, I discussed this last time. We reached the center pretty quickly. We had a score of 66.4 or whatever. And this was our best run effective distance and best number of turns. Right. And we determined that, okay, there's no point in moving from that, you know, based on how much our bot estimates it should move. So it's just gonna, you know, it's gonna go through a lot of the maze in order to just find the minimum distance. Yeah, and then our score is effectively 87.3. So what are some ideas you guys have that we could implement in order to keep that score as low as we can, you know? And I also said I would share one of my ideas. So one of my ideas is that we assume that from the center, we will need to make at least 3 searches in order to reach that minimum distance, right? So okay, our supposed best number of moves is 22, right? Take out a calculator here. Right, current score is 66.4, 66.3, whatever. I'll double check actually. 39. Sorry, 39. 38. Oh my goodness. 38 plus 22 plus 1 times 38 plus 22. Okay, it's just 66. All right. So, supposing it's 66, right? Our current score is 66 once we like reach the center. Right? We want to keep that score. So what do we need to do? Like, how do we determine that we should stay in the center? So my idea was we assume that we will need to go this distance about 3 times, right? And how do we know how many turns we'll probably take? All right, so what we do is we compare the number of turns to the number of times we move forward, right? Actually, should do. So we have 22 turns. Our best run turns is 22 over 38. Right, so that's the ratio of turns to moves. And when we multiply that by 22 here, because you know we're assuming we're only going to have to move 22 times. Right, 12 point whatever, okay? And then you add that to 22. Okay, you get 34 point whatever. And then you assume that you will do this same thing, right? 3 times over, right? So you'll have to move from here, okay? So that's 1 addition. And then here, that's 2. Then here again, that's 3. And here again, that's 4. and here again, that's 5, then here again, that's 6. That's 3 whole trips. Right, so we're assuming that we will make 3 trips. So we multiply this by 6. Right? And that's going to be added to our total distance. So this plus 38 plus 22. Right? Yet that's your total distance. You multiply that by 0.1. Okay? You end up with that. And you add that to what you're assuming to be your best run distance. So 22 plus, I think we had 12 point something for our estimated number of turns it would take. I'm just going to say it's 13. All right. And then this, we get a score, an approximated score of 61 point whatever, right? That's pretty close to this score. What we want to do is we want to make sure that whatever score we're assuming we're going to get needs to be at least more than 10% better than the score we already have, right? This is not more than 10% better. Because if we divide this by 66, no. It's still within 90. It's like 93% of what we have right now. So it's within 7% of our current score. That's not good. We want at least 10. Right? It needs to be at least 10% better. So that's the idea I had, to make sure that our bot doesn't move from the center. So are there any thoughts on that, or do you guys just not have time to think about that, or maybe you forgot? That's all right too.
That's pretty interesting.
Yeah, it took me a bit to come up with that when I was first writing this code. I'm like, should I implement it? I was like, nah, I'll save it for a later date.
Yeah. I just want to go over the whole scoring thing again on my own before I say anything. Yeah,
so how the scoring metric works is that you take the best number of turns you have plus the best number of effective run distance you have plus the best number of turns. And then you add that to 0.1 times the total distance plus the total turns.
So if you let it run for a while, the total distance would be like a lot higher.
Yes.
Okay, that makes sense.
So yeah, my idea is that we have to assume that we're gonna have to, go through the entire maze for the best distance at least 3 times. And then if that estimated score is not at least 10% better, then we don't go for it.
And so we could just use the score. Like, can we use the score of the first run?
Yeah,
like,
so
is that how it works? Okay.
Yeah, we're comparing it to the score our bot gets when it reaches the center.
Yeah.
And then, we're going to estimate based on this value right here, what's going to be our future score. And we decide to move based on that.
Oh, okay. Yeah, that clears it up.
Okay, so yeah, if nobody has any ideas right now, think on that for a bit. Review the rules if you need to. And come back to the meeting. Hopefully we have some fresh ideas for that. I'll leave a bit of a reminder in chat as well. So
yeah.
If everybody's good, if everybody doesn't have any troubles with installing Qt, that's the end of the meeting, and I hope to see you all again next week. I'll be confirming registration, and I will be registering on the meeting itself when we have the meeting.